So this is the last video in the Fritz John series, and in it we'll be deriving the Fritz John conditions. Now recall that the problem was a constraint optimization problem in which you want to minimize f of x, where x is some vector of length n, subject to both inequality and equality constraints. So I don't understand this fully, but I'll try to explain it. So when you're trying to minimize f of x subject to the inequality and equality constraints, there are certain directions we'll call D that are feasible for when you want to go in directions in which you minimize f of x. So one property is that the directional derivative in the direction of this feasible direction has to be less than 0. So when you're going in one of these feasible directions, you want to go down the slope. So that's in the direction of the the minimum. Then also you want to stay on the manifold. That's what these two conditions over here say. So the directional derivative of g in the direction of d is less than or equal to 0. Well, that's only if gi of x is 0. Because if vi of x is 0, then you really can't go above that, since it has to be less than or equal to 0, meaning that you have to go in a direction that's gives you less than 0 or equal to 0. So these are called the active constraints, sets of I, such that gi of x is equal to 0. This is the another constraint that says that you have to be on the manifold. It's the directional derivative of h in the direction of d has to be 0. That's because you have to stay 0 you have to stay at 0 for all the h j of x conditions, equality conditions. So yeah, but this can also be expressed as, for all j, the directional derivative of h in the direction of d is less than or equal to 0, and the negative of the directional derivative of h in the direction of d is less than or equal to 0. So both of these are less than or equal to 0. One is positive, one is negative, and represents this condition over here. So now let's choose a special point, which we'll call x star. And x star is a local minimizer, meaning that you cannot go any further down, at least locally. So if we're to choose the direction in which you go down, well, you can't, because it is a local minimum. So no direction in the hypersphere at x star can you go down, at least infinitesimally. If you're to perturb it in an infinitesimal direction, d, then it cannot be less than 0. The change in altitude, you could say. But these conditions are just being on the manifold, so they don't really matter, but this condition cannot be true. So now recall Farka's lemma. It states that if 2 is not true, then 1 must be true. And that'll be important for the upcoming logic. And in this yellow box, we can also restate this as C transpose X is less than 0, where C is negative B. Farka's lemma, A transpose would be this gigantic vector, or actually matrix, because it's a vector of vectors. X would be D, your feasible directions, and negative B would actually be lambda naught times the gradient of f of x star. Now, why say lambda knots? Well, it's because you can scale by some lambda knot is greater than or equal to 0, and the inequality condition corresponding to this would still be true. So if we put this all in the form of the dual condition, or condition number 2, then it cannot be true because of that the directional derivative in the direction of d of f is less than 0. That cannot be true. So therefore, all 3 of those conditions cannot be true. Therefore, 1 must be true, the primal condition, in which you have multipliers of matrix A is equal to B, where these multipliers are greater than or equal to 0. I'm sorry, the vector lambda, yeah, these multipliers are greater than or equal to 0, yeah. So I was also going to say that, going back to this lambda knots, any of the conditions can be scaled. But if you were to try to scale the conditions for the inequality and equality constraints, then it would just be absorbed into the x right there. So this lambda knot cannot be absorbed, and therefore we express it explicitly, if that makes sense. So over here we have the matrix A. It's no longer A transpose, but A times the vector lambda of greater than or equal to 0 constants, or sorry, scalars, where I1 to Ik are members of the active inequality constraints at x star. There are p equality constraints over here, and yeah, I already said that. So you'll notice that we have the positive and negative equality constraints, or they're actually positive and negative because we converted them to inequality constraints, but together they form equality constraints, a set of p equality constraints, which is equivalent to 2 times p inequality constraints. So what can we do over here? What we can do is that you'll notice that when you sum these scalars multiplied by the equality constraints that we converted to inequality constraints, you notice that we get pairs for each j. We get pairs such that you have mu sub j times gradient of h sub j of x star minus mu sub 2 times j times the gradient of h2j of x star. Yeah, you'll get pairs of what that subtracted from this. So you can group up these scalars and just multiply by a gradient of hj of xr on the right. And note each of these scalars has to be greater than or equal to 0. But when you subtract them, they can be any real number. And we'll call them nu sub j. So, since we absorbed those coefficients, we can kind of reduce it to just p of these equality constraints. No more, you don't have to do the negatives and positives, just the positives, times these new scalars from 1 to p. That can be any real number. And this also implies that lambda sub 0 and lambda sub I are greater than or equal to 0. But you'll also notice that I1 to Ik being members of the active inequality constraints at x star, that's the same thing as saying that all of these i's, for all of these i's, lambda sub I times g sub I of x star is equal to 0. Now, why is that true? Because say that your inequality constraint is active. That means that g sub I of x star is 0. Then this would have to influence it by being either 0 or non-zero. It depends, because the goal is for lambda to influence it such that the directional derivative in the direction of d of g sub I, or the gradient of g sub I, is less than or equal to 0. And then when g sub I of x star is inactive or negative, then lambda sub I would have to be 0, and it doesn't contribute to this sum. Now, why doesn't it contribute to the sum? I'll have to think about that a little bit more. It's just something to think about, but I'll leave it there. And so those are the Fritz John conditions. And this is the last video in the series, I'm pretty sure. So I'll see you in the next video, whether that be observability / controllability or some other concepts. I'll see you in the next video.